Hi everyone, my name is Sara Oliveira and I'm here today to present you the paper entitled Cyclic Behavior of Steel Beam to Column Joints and Calculation Tools. So, I will present you the scope of this research work, a brief literature review on the behavior of joints under cyclic loading, the proposed cyclic component method and its computational implementation, an illustrative example, and finally, draw some conclusions from this. Unlike static monotonic loading, it is not yet possible to predict the moment rotation response of steel joints under cyclic loading using the component method. Therefore, the usual approach is to develop multi-parameter mathematical expressions that are able to reproduce the range of hysteretic behaviors. However, such approach relies purely on statistical calibration without a mechanical background. The relevance of this problem was recognized by EcoJoints project, whereby the development of a cyclic component method is addressed. Note that this software is mostly addressed to experts who fully understand the complexity of steel joints subject to cyclic loading and know how to model the mechanical behavior of each critical component. The structural behavior of steel joints under cyclic loading is characterized by hysteric loops with progressive degradation of strength and stiffness, often combined with pinching effects. The Richard-Abbott mathematical expression can reproduce the phenomena shown in the previous slide. Furthermore, this model is adopted because of the advantage of a continuous and differentiable function within each ascending and descending branch, unlike a trilinear model, which can cause convergence problems at each change of slope point, especially when using incremental iterative procedures. The modified Richard-Abbott model comprised a large number of parameters to account pinching effect, stiffness and strength degradation, and strain hardening. In total, 30 parameters can be defined, 15 for the loading and 15 for the unloading branch. The component model of Figure 1 is not able to deal with sagging bending moment, as different components are present, and vice versa for Figure 2, which is not able to deal with hogging bending moment. The proposed model in Figure 3 overcomes this problem by defining components that present distinct behavior in tension and in compression that only becomes active in tension or in compression. In the cyclic component model, two groups of components need to be characterized, non-dissipative and dissipative components. Both types contribute for the joint deformation, but only the second type contributes for energy dissipation. In addition, the force deformation laws of all the components were implemented, where appropriate, with tension only or compression only behaviors. For instance, the component column web in tension is modeled with a mechanical behavior which the component it is only active in tension. When it is not active, it is assigned a linear law. Simulating the behavior of steel joints subjected to cyclic loading is a complex job. The cyclic model has to be able to reproduce this direct behavior, that is, the load reversed at any level of rotation, including the degradation of the performance of the joint as the number of cycles increases. Therefore, sophisticated mathematical models are used, such as Richard-Abbott expression. The developed software Cyclic was implemented in MATLAB with input and output files in Excel files, and is divided in three modules. The curve fitting, which computes the best fit for the Richard-Abbott parameters, such as initial stiffness, post-limit stiffness, resistance, and shape parameter, of the force deformation curve for each component extracted from finite element models or experimental tests. All parameters obtained through curve fitting are used as an input in comp model calculator. This model computes the quasi-static and cyclic nonlinear behavior of beam-to-column joints. And finally, Results Analyzer is a tool to help the user to analyze the output results of comp model calculator with an interface which allows the user to perform a visual assessment of the several components at the same time in terms of force deformation curves. The curve fitting computes the best fit of the numerical or experimental results to the Richard-Abbott mathematical expression. In addition, the parameters obtained through Eurocode 3, such as initial stiffness and resistance, can be imposed so the remaining Richard-Abbott parameters can be computed in this model. The comp model calculator is the central core of the program, and it was developed to compute the quasi-static and cyclic nonlinear behavior of beam-to-column joints, based on an incremental iterative procedure with displacement control. It is a general tool and thus may be used to predict the behavior of beam-to-column joints with arbitrary dimensions falling within the limits of application of Eurocode 3. Following, it is presented an illustrative example of application of the cyclic component method for a beam-to-column joint, which was previously analyzed through a finite element model using ABAC software. The selected beam-to-column joint is a double extended end plate with 25 mm thickness without stiffeners, with 6 bolt rows, and was selected within EqualJoint project. The first step is identification and classification of components. The second step is the computation of the strength and initial stiffness according to Eurocode 3. Following, characterization of the joint components is performed using finite element models to extract force deformation curves of each component in accordance with August's proposal. In the fourth step, those curves were introduced in curve fitting to compute the Richard-Abbott parameters. Then, in comp model calculator, a mechanical behavior is assigned to each dissipative component in order to guarantee that the components are only active in tension or in compression as it is expected. Assigning a deformation limit, delta limit, equal to 0 ensures that the component is only active where it is needed, tension or compression only. Then the slope beta is equal to 2% defines the line when the component it is not active. Only the component column having shear is active in both tension and compression. These figures show the bending moment rotation relation for the beam-to-column joint computed from ABAC's finite element model and with Cyclic, showing in general a good agreement. The main disagreement in the moment rotation curve of the beam-to-column joint is the slope of the unloading branches for a bending moment close to 0, for both sagging and hogging moments. The bending moment rotation computed with Cyclic shows high pinching, but the bending moment rotation computed with ABAC does not. This difference is mathematically explained by the change of active components. For example, the MB3 behavior was assigned for all dissipative components in tension, making it active only above a linear behavior assumed with a slope of 2% of the initial stiffness and thus yielding that behavior. The force deformation curve for the column having shear and the moment rotation curve of the connection, both showing good agreement between Cyclic and ABAC for the initial stiffness, strength, and post-limit stiffness. In a summarized manner, in order to develop the cyclic component method, the following steps were taken. Identification and classification of the components according to the Eurocode 3. Assembly of the mechanical model. Analysis of the joint using a refined 3D finite element model. Extraction of the force deformation curves for each component. Computation of the Richard-Abbott parameters using curve fitting. Assign a mechanical behavior to each component. Computation of the cyclic behavior of the joint using comp model calculator. And finally, results. Moment rotation curves for the global behavior of the joint and force deformation curves for each component. This paper summarizes some advances in the development of a general method, the cyclic component method, for predicting the cyclic behavior of steel beam-to-column joints. The cyclic component method is a component-based method that uses the principles of the component method coded in Eurocode 3, and thus provides an adequate basis for the design of joints by allowing a simple assessment of the influence of key geometrical properties of the joint, both diameter and plate thickness, etc., on their cyclic response. The development of a cyclic component method requires several steps for which investigation is being carried out, namely, procedures for the extraction of the cyclic behavior of components from experimental tests and/or refined finite element models, analytical models for the cyclic behavior of components, for example, the modified Ricardo model, and the calibration of their parameters, layout of components in a suitable mechanical model and mechanical behaviors, model consistent with the layout, and stable numerical procedures for the cyclic analysis of the joint mechanical model. The results gathered so far allow not only a deeper insight into the cyclic behavior of steel beam-to-column joints, but also have already proven that the cyclic component method provides a reasonable simulation of the joint behavior for the cyclic analysis and embodies a clear and powerful tool. Thank you for watching. Any questions?